implicit function. Okay, so mesh, point cloud, and voxel they belong to explicit representation, but today we will cover implicit function. So the implicit function definition, it tries to learn a function to classify arbitrarily 3D points as inside or outside the shape, right? So there is nothing about some explicit geometry. So it's just there is only function that takes a coordinate of a point, position of a coordinate. This one is a three-dimensional space, right? X, Y, Z to binary. That is the implicit function. We are trying to classify whether that point is inside or outside of a point. And then the surface of 3D object can be a level set. Level set is this kind. Here's we have set, right? We have set, and we have function, and then we have some predefined threshold. That is level set. Level set of 0.5. This is level set of 0.5. So 0 means it is inside of a 3D object, and 1 means it is outside of 3D object. Then 0.5 might be, we can approximately say that 0.5 might be surface of a 3D object, right? So that is the way that we can represent 3D surface of object with this kind of implicit function. It is quite different from explicit representation, right? It's quite different. Point cloud, mesh, voxel, we always have explicit definition of 3D space, and then like a triangle mesh or volumetric space or point. But here we indirectly define some 3D shape using a predefined function. We can see some example. Let's see the example first. This kind of ones. So here these are some predefined implicit function. This is a sphere, right? Sphere in three-dimensional space. So let's say we have function x, y, z. And then if we pass a 0.0.0 f, that is smaller than 0, right? That gives us -1, right? So that is smaller than 0. And if we pass 2, 2, 2, that is larger than 0, right? So that we can say that 0.0.0, we have predefined function, so that is inside of object because the sign of that function is negative, and 2 by 2, 2, 2, that gives a positive value. That means it is outside of surface. The sign, the value is positive, right? So using this kind of function, predefined function, we can represent 3D surface. Or there are more examples, like a more complicated shape we can present with implicit function. And so the definition is represent a surface with a learned function that classifies arbitrarily 3D points as inside or outside of a 3D shape. The good points are topology free. So in case of mesh, we have predefined topology, right? Number of vertices, mesh, number of vertices, and triangle face, right? Mesh assumes we have a predefined topology and then do something based on this kind of predefined topology. But volume or implicit function, they're topology free. It can represent any shape with function. And then memory efficient, because I will explain this a little bit detail later, but in case of volume, we need to store all the voxel values. For example, 1K, 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 right? We need to store all this kind of, so we need to store 1K cubic points, 1K cubic data to store voxel, right? But in case of function, actually we need to store just this one. I mean, this is the only thing that we need to store, right? Just there can be many ways to store this function. For example, assuming we have polynomial function, then the only thing we need to store are just this one. square, 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 and 1. Just 4 integer is enough. If we assume a polynomial function, then just 4 integer is enough. So quite memory efficient. We only need to store very few numbers, right? So it is memory efficient than voxel. But the drawbacks are, these are related to nerf. We need to evaluate all points, whether they are inside or outside of the shape. And for example, I mean, what we have from this implicit function is just a function like this. And actually, to determine whether a point is inside or outside of 3D shape, we need to pass these positions, 0, 0, 0, pass to this function to get sign of this function, right? We always need to do something. It is not O1. I mean, getting value is not O1. Explicit, like a mesh, volume, point cloud, getting something is O1. We can simply retrieve, but implicit function, we need to do some calculation to check whether this point belongs to inside or outside of function. So implicit, not O1, right? So we need to evaluate all points, whether they are inside or outside of shape. That it means time inefficient. So it is memory efficient. In terms of memory, it is quite efficient. In terms of time, it is not efficient. It is quite slow. It's quite slow. Training inference of fields quite slow. So there can be predefined functions like a sphere, a donut shape, heart shape. There can be many predefined functions, but we are always interested in arbitrary shape, right? More complicated shapes. How can we represent such kind of complicated shape with implicit function? So that we can introduce actually sign distance field. And this one shows the visualization of implicit function. So store grid of values approximating function, and then surface is found where interpolative value equals to 0. So these values are negative, right? These are negative. These are negative. These are positive. And then somewhere between negative and positive, which one x making the function to 0, there might be surface of 3D object, right? That is the way how this implicit function can represent 3D surface. And there are some examples like sign distance field. This is the representative example of implicit function. And this shows 2D sign distance field. So there are 3 words, right? Sign, distance, and field. So sign means there are positive and negative values. Positive means usually outside of 3D shape. You can see here, this positive, they are positive, right? This greenish, bluish pixels have positive values, and reddish colors are negative values, right? So typically in sign distance field, positive value means outside of surface, and negative means inside of surface. So this is why we have signed here. And distance, each pixel has distance from each point to the surface, shortest distance. So let's say this pixel, shortest distance might be, no, this is not very easy to see, this one. Shortest distance might be this one, right? So the value of this pixel, 91.7, is distance between this point and closest surface point. That is why we have distance here. And field, I think you're familiar with gravity field, right? So field is from physics, and the definition of field is a physical quantity defined at every point in space and time. So gravity field, what is gravity? I mean, just the example, gravity field. We are living in, 4D space and time, right? And for each point we can get gravity value. So that is just the same. Field, a physical quantity defined at every point in space and time. For every space, all pixels in the 2D or 3D point, 3D space, it has some value where the value is distance from each point to the surface. So that is the reason why we call this field. For every point in the 2D or 3D space, it has its value. In case of SDF, the value is distance from each point to the surface. there can be many fields, there can be many fields. Sine distance field is just one example of field. There are many fields in physics, math, or AI. There can be many fields. Nerf is also field, and we will study nerf later. Here, F is field, neural radiance field. So field is not some typical, some specific example of this SDF. Field is very broad concept, and field is just a physical quantity defined at every point in space and time. So sign means they are positive and negative, and distance means for each pixel, its value is distance from each point to the surface, shortest distance, and field means a physical quantity defined at every point in space and time. And for each point, it returns, as I said, shortest distance from it to the surface. This point, the value is shortest distance between this one, between itself and the 3D surface. Or this one, maybe this distance, or this one, maybe this distance. So each pixel always have a shortest distance from itself to the 3D surface. That means level set equals to 0, 0 level set, which makes fx equals to 0 becomes the 3D surface of 3D object, right? What does this mean? In sine distance field, the output of this function is the distance between a point and surface, right? If it's 0, then distance between a point and surface is 0. That means it's just on the surface, right? Distance is 0. Then a point whose SDF is 0. That means such points are on the surface. The distance is 0, right? So we can get surface by getting some points which make SDF equals to 0. Set of points where fx equals to 0. That is the surface. Set of points which makes SDF equals to 0. That is surface, right? By definition. Because points which make SDF equals to 0 means distance between point and surface is 0. That means a point is on the plane, on the surface. So that if we can get a set of such point, then that becomes just a surface, right? That is, in other words, we call this level set equals to 0 or 0 level set. And so that is the way how can we define SDF. There are some variant of SDF, like a truncated SDF, TSDF. You do not have to remember this. There are many variants of SDF. SDF is very widely used in computer vision to represent 3D or 2D shape. And as I said, sign gives us whether the point is inside or outside of the 3D object. As I said, positive sign, that means outside of 3D object. Negative sign, that means inside of 3D object. So SDF is the example of implicit function. If we can get this f function that takes a position of pixel and outputs distance from that point to the 3D surface, if we can get such function, then that's all. That is the way we can define 3D object in an implicit way. That is called sine distance field. Okay, clear? And based on this sine distance field concept, back in the day, like 6 years ago, CPR 2019, deep SDF was introduced. Deep SDF is a way to represent getting SDF using neural network, and that is the foundation of NERF. Very similar to NERF. NERF was introduced in 2020, so it is a kind of early approach or early attempt to try NERF. But the basic concept is very similar. Deep SDF and NERF is very similar. So here, as you can see, we have a neural network. This is neural MLP. We have a neural network MLP that takes a coordinate and then outputs SDF. Why we are doing this? Because if we get, as I said, if we can get this function f, then that's all. We can represent 3D shape with neural network, with this function, right? So then how can we get this function? Once we can get this function f, then we can represent 3D object using in an implicit way, right? Then how can we get this function? Deep SDF gives a answer. We can train a neural network that takes XYZ coordinates and outputs SDF value. In this way, we can get a function f. Function f is just a neural network. Training a neural network mostly consists of MLPs that takes XYZ coordinates and outputs SDF value, right? Takes XYZ coordinate, outputs SDF. It is a little bit advanced one. You can just ignore this. Very basic design is just taking coordinate and outputs MLP. And then, assuming we have ground truth 3D object, assuming we have ground truth 3D geometry, then we can train neural network with this loss function. I mean, we can simply, this is the output of, this is output, and this is ground truth. We can easily get ground truth if we assume we have 3D object geometry, then we can get ground truth SDF, right? For example, if we are interested in this point, then assuming we have this kind of 3D mesh, then we can get distance between this point and this surface. We learn a shortest distance between point and line in high school, right? This is y, x, this is point. We know the distance, right? This distance d. Distance between a point and line, shortest distance in 2D space. We learn in high school, right? We can simply extend the 3D case, but then we can simply get shortest distance between a point and triangle face in the 3D space. That becomes ground truth, SDF. And then this is output of neural network. This is output. This is ground truth. Ground truth or target. And then we can simply minimize L1 loss between estimated and ground truth SDF. Once we finish the training, then that's all. Then we can represent this any complicated 3D shape with neural network weights. This is a new way to represent 3D object with neural network weights. As I said, it is much more memory efficient. In case of voxel, still maybe comparable or a little bit heavier than mesh, but much memory efficient than voxel. Because voxel, as I said, if you're trying to save this bunny in a volume, then we need to store all this 1K voxels, right? We need to store all these voxels, whether it is empty or not. We need to save all these voxels. And as I introduced, this one maybe takes 4 GB, right? But deep SDF, what we need to do is just simply saving weights of this neural network. We have weights of this MLP, right? Learnable weights in MLP, they are already optimized so that we can simply store neural network weights, right? In this way, we can save, this is much more lighter than 4 GB typically. Because MLP, this one is very shallow MLP, just maybe 5 layer, very simple MLP. So it's much more lighter. In terms of memory, it is much more lighter than saving all voxels in volume space. So that deep SDF gives a new way to represent the object with neural network weights. But as I said, it is time inefficient. Why is it time inefficient? Because we need to, let's say we load weights of neural network. We load weight of neural network, and then, but we have no idea how what this neural network is trying to have in 3D space. We do not have no idea what this neural network can represent any 3D object. So one way is we let's define a voxel, and then let's say we pass all this point, all the coordinates to the neural network, and then get SDF value. And then we have something, right? Passing all the points to the neural network, and then we get SDF value of all points, then we can get 3D geometry, right? So that makes we need to make a forward pass of neural network for all points, sample points. That makes, that requires us to do the inference of many points in 3D space using neural network, right? Let me clarify this again. So in case of voxel, let's say we loaded all the voxel 4 GB, and then we are interested in this point. Let's say we're interested in this point. In case of voxel, we can just simply retrieve. Let's say we have volume x, y, z. V is a three-dimensional tensor, and then we can simply take a voxel value, whether it is occupied or not, by just simply taking x, y, z, value at the x, y, z position, right? This is just the O1, but I'm implicit. We loaded weight of neural network, and then we need to pass it x, y, z. Right? This one, there's nothing to do, just simply retrieve. There's nothing to compute, just O1. But in case of neural network, if we're interested in this point, then we need to make a forward pass of this point to the neural network, and then check whether this point is inside or outside of the object, 3D object. So inside of neural network, we need to do some computation, right? We need to do NLP, multiplication, addition inside the neural network, so that every point needs some computation to get SDF value. So that makes time inefficient compared to voxels or mesh or point cloud. That is drawback of implicit function. It is much more memory efficient than voxel, but very time inefficient, very slow. Is it clear? Any question about this one? No? So this is the application of SDF. This is introduced in 6 years ago about 3D human reconstruction from a single image. So this work shows the good point of implicit function compared to mesh, volume, and point cloud. So let's say we have a single image of human and then try to lift the human image to 3D space. And then which representation we can try. We learned this one, mesh, volume, point cloud, and implicit. We have 4 options, right? Which option are we going to try? First, mesh. What about mesh? Mesh is good, but as I said, clothes have diverse topology, right? We can wear pants, we can wear skirts. Pants and skirts have different topology. This is pants. This is skirt. No, skirt. They have different topology. And this is shirt, and maybe we can wear some. This is jacket. This is jacket. This is jacket. We can open this one, right? This is jacket. So there can be many topology in cloth, so that neural network, it assumes the output dimension is fixed, right? But number of vertices, triangle combination, all those stuff could depend on cloth types. So that, unfortunately, mesh is not a good representation for human. Naked body is good, but cloth, there are too many combinations, so mesh is not good. Volume is topology free, right? But unfortunately, it is memory inefficient. To get very high detail level, like a wrinkle of clothes, we need very high resolution volume. But 1K by 1K by 1K volume, it already takes 4 GB. It is too memory inefficient. But if we compromise the resolution of volume, like 256, 256, 256, too low expressiveness, no wrinkle, just a flat surface. So volume is not a good option. Point cloud point cloud is too sparse. It is not good for photorealistic rendering. But implicit function, it is topology free, so that it can represent any type of clothes. At the same time, memory efficient, so that we can get high expressiveness. We can get wrinkle of clothes or any geometric pattern of clothes, we can get them. And very dense, so that this one shows the good point of implicit function to represent human, especially clothes. So that from a single image, it query random 3D point, assuming human is at some canonical space. It query random points, and then train neural network to output occupancy and texture of each point. Right here are inside, outside, and RGB. Right. So we query many 3D points in the 3D surface, and then pass them to the neural network, and then the neural network for each point, it outputs whether that point is inside or outside of the surface. Maybe we can simply do binary classification, 0 and 1, and then RGB value. So that is the good point of implicit function. Topology free, memory efficient. Memory efficient means we can get high resolution representation, and that makes high expressiveness, right? And dense. The limitation is that, of course, time. It is very slow to get surface. You can see here, marching cube. Marching cube is the algorithm. Marching cube is an algorithm that gives a set of x which make SDF equals to 0. So assuming we have a sign distance field, marching cube is the algorithm that gives us a set of point x that makes SDF very close to 0. It means we can get 3D surface from this implicit function, right? Using marching cube. Marching cube usually take a few minutes. It already takes few minutes, right? So typically for the real-time application, we need 30 frames per sec, for 30 frames per second. But few minutes for a single image, it already takes few minutes. It's too slow. And let's say we have marching cube here, but for limited rendering to get images, it is too slow. So that it is good, topology free, so that we can represent diverse clothes, memory efficient, high detail, dense, but still limitation is too slow. Marching cube already takes few minutes. I think this work is quite good. Actually, Shunsuke was my colleague when I was in Meta. He's very good. And this work is very seminal work. And so implicit function, this one gives a new way to represent 3D human reconstruction. This one is also clear? Good. And let's proceed to nerve. So we can see field as well here, right? Nerve is introduced in 2020. And we need to train nerve. So nerve is also a neural network based, because we have neural, right? So we need neural network. What we need to train is just multiple images of a single scene and camera calibration, camera intrinsic, extrinsic parameters. So you can see there are many multiple images. You can see there are multiple images, and all the camera needs to be calibrated in advance. So these are what we need to train nerve. And after training nerve, what can we get? 3D images of a single scene. Let's say we have some 10 or 20 images of a object, and then once we optimize nerve, and then we can render this object from any viewpoint. That is the what we can get from trained nerve. You can see input image. There are multiple images and camera calibration. We can optimize nerve, and then we can render new view. That is called novel view synthesis. Is novel view synthesis. This is what nerve is doing. from multiple images of a single scene and camera calibration, camera parameters. We are trying to get neural network that can represent this 3D scene, and then once we get this neural network, we can render images from any viewpoint. That is what we can get, what we can do with NERF. So these are input and output of NERF. So we have neural network, and here are input and output. Input, they are 5D input, 5D, scene location. We learned implicit function, right? Quite similar. It takes a XYZ coordinate of in the world coordinate system, and then viewing direction, and then neural network takes this positional and viewing direction information, and then for each point, it outputs color and density. We will see one by one. So scene location, assuming an object is some canonical space, we sample points around the object center, and that just becomes the input of neural network. And these are all the input of neural network, scene location in world coordinate system. And then viewing direction. Why do we need viewing direction? I introduced this kind of specular reflection very early of this course. Depending on the viewpoint, the color can change, right? I mean, for example, if I have this object, that might change my view, where I see this object, the color changes. There are reflections, right? So specular reflection, or there are some view-dependent color changes. So that is the reason why we additionally include camera-to-point vector in world coordinate system. So these are input, scene location, and viewing direction, where scene location is the locational point that we're interested in, and viewing direction is assuming we have some desired viewpoint, and then we can get camera to point in world coordinate system. So there are view-dependent color changes. Object is fixed, but depending on which direction you see the object, the color changes. And output is color and density. Color of the point, and density is just a range of 0 to 1 with sigmoid exponential function. Maybe you can define 0 is empty and 1 is occupied. That's all. And then that is the input and output of neural network. So the scene location and viewing direction are input, and outputs for each point, for each 5D input, it outputs color and density. Where color is just the RGB color of the point, and density is whether it is occupied or not. And then how can we train this neural network? In DeepSDF, let's recap DeepSDF. DeepSDF, how can we train this? We assume we have 3D object geometry, right? We assume we have this kind of mesh 3D geometry, so that for each point of interest, we can get ground truth SDF value, right? But assuming we have good 3D geometry is kind of not very trivial. I mean, getting good geometry is not very trivial. To get 3D geometry, actually, we need to do multiview stereo that we learned, right? It is not very easy. So there can be errors in 3D geometry. Reconstruct 3D geometry can have errors. So we assume we do not know 3D geometry. When we train NERF, we assume we do not have 3D object geometry. All we only have is, as I said, multiple images and camera calibration, that's all. We do not require 3D object geometry. So we do not know 3D object geometry, but only supervise rendered images with image loss. That is how can we train your NERF. So here, 5D input, point and direction are passed to neural network, and then outputs RGB and density. And then we render some images. And then as we have multiple images, right? We have multiple images, so that we render images to some viewpoint, and then we can just pixel-wise compare the rendered image and captured image. And we can minimize distance between rendered image and captured image. That is the rendering loss. Comparing rendered image and ground truth image, minimize distance between them. And assuming we have multi-view images, then we can optimize the neural network. That is how we can train this neural network. Then what is volume rendering? So volume rendering, this one shows volume rendering. So volume rendering, the first thing we need to do is like, let's say we have, let's say this is camera, and this is the object. And then so we know desired viewpoint and desired resolution, right? So that we can define pixels in screen space. And then for each pixel, we shoot a ray, right? We shoot a ray. That is called ray casting. We cast a ray for each pixel, the desired screen space from the desired screen space along the ray. We cast a ray, and then we do the ray marching. Ray marching means going and going, right? We sample points T along the ray. This is ray. Along the ray at fixed or adaptive intervals. So starting from this pixel position, we do this one, keep marching with fixed or adaptive intervals. That is called ray marching. And we actually have initial points Tn and final points Tf, where n represent near and f represent far. Because we cannot consider all the infinite space, so we need some range of the 3D space. So that is defined by hyperparameter Tn and Tf. And so we cast a ray and the ray marching, and accumulate contributions along the ray using transmittance. So transmittance means how much light survives from Tn to T. So for example, let's say we have this object, and we shoot a ray like this one, and then this ray meets this surface, and then we cannot see surface behind this surface, right? Because light after the surface is not survived. Once light meets the surface, then light just ends, and behind the surface, no light survived, right? That is the reason why we cannot see back of the surface. So, but in empty space, let's say I shoot a ray, but in empty space, all the light survive, right? If there's smoke around here, then maybe many lights will not survive. Light will, many of this 3D surface might be occluded by this smoke. But in the empty space, most of the lights survive and then intersect with this surface. But we cannot see behind of this object because there's no light survive after this surface in ray marching. So transmittance means how much light survive from Tn to T. It accumulate transparency along the ray, right? Along the ray, it accumulate transparency. T equals to 1 means fully transparent so far. It's totally visible. T is very small, almost fully observed or blocked. We learned density, right? We learned density here. And then T is a exponential of minus density. And they used to weight each sample contribution during volume rendering. And this is the mathematical equation of volume rendering. This one is density. We learned density, right? Density, color. And this is color. And this is transmittancy. Where definition transmittancy means, as you can see, Tn integrate from Tn to T. It accumulates impact of estimated density from the initial point to the current position, right? If T equals to 1, then so far there is nothing blocking this light. Because density from Tn to T is almost equals to 0. Then T equals to 1, right? If we have exponential. So if we density from Tn to T is almost 0, then T becomes 1, and T becomes 1, fully transparent so far. So nothing is blocking. That is T equals to 1. So it keep accumulating the impact of estimated density from Tn to T. That becomes transmittancy. And then density and color are just the density of color of the current point, not accumulated value. That's the density and color. You can see there's only T. There's no accumulation, just the density of a point T, color of point T, right? But on transmittancy, it's just accumulated one from Tn to T. So we keep accumulate the color by weighting about the transmittancy. And the accumulated color becomes the final color, that is the weighted sum of sample color. Then we can get color of this pixel. So for each pixel, we shoot a ray and then do ray marching. And then for adaptive or fixed interval, we keep calculate this. We calculate this, we keep calculate this. And then once we meet a termination condition, for example, if t equals to 0, t is very small, then we stop the ray marching for that pixel. That is how can we get color or any other features in the screen space using volume rendering. This is volume rendering. The reason why we have volume here is that it can be used for voxels. We learn voxel, right? I mean, we can use this volumetric rendering for voxel as well, or implicit function. And that is this volumetric rendering is the thing that I introduced in the other Unreal Engine. We use volumetric rendering in Unreal Engine to render some smoke or some hair, fire, right? We use such functions are based on this mathematical equation, volumetric rendering. One thing we learned about rendering is mesh, right? In previous class, we learned mesh. So what is the difference between mesh rendering and volume rendering? So this is mesh rendering. This is mesh rendering. This is mesh rendering. And as I said, we have rasterization, texturing, and lighting, right? Rasterization means we, for each pixel, we project triangle to the screen space, and then each pixel triangle face, index, and barycentric coordinates. And then we get color from UV map. That is what is happening in mesh rendering. Here, for the mesh rendering, we need mesh topology, vertex coordinate, triangle face in UV map, and vertex coordinate. So it is very different. Mesh rendering. Actually, rasterization is a little bit similar. For the rasterization, let's say we have desired screen space, and then we have some 3D object, and then tries to rasterize. Then we shoot a ray as well. We shoot a ray, and then shoot a ray until it intersects with some surface. If it intersects with some surface, then the ray marching is terminated, and just get intersecting the triangle face index of intersecting triangle becomes the output of the rasterization. So that means, mesh rasterization, it does not take care about the empty space. It just do ray marching until it intersects with some 3D surface. And then once you intersect with 3D surface, and then you can get triangle face index and barycentric coordinates, and then that becomes the output of rasterization. But the volumetric rendering, it keep accumulating the density, color, weighted by transmittance, right? With the fixed interval, adaptive interval. So shoot a ray, and then there's a fixed or adaptive intervals, and then keep accumulating density and color weighted by transmittance, and then the final color is obtained when it meets termination condition. And termination condition is when t is almost 0, then it terminates. So point cloud is not used for rendering. Gaussian splatting is based on point cloud, but point cloud itself is not used for rendering because it is too sparse. So there are two rendering pipeline. Mesh rendering pipeline, volume rendering pipeline. They are very different. Mesh will require this kind of predefined topology and do rasterization and texturing based on UV map. That is what is happening in mesh rendering pipeline. But the volumetric rendering pipeline, we do not take care about topology, just do ray marching and then accumulate the color based on transmittancy, and then that becomes the final color once the mid termination condition, where termination condition is transmittance is almost 0. And then once optimized, we can render new images, as I said. Once optimized, we can get low value images. And then we define desired screen space and then just use volume rendering to get low value images. So here, this example is very time inefficient, as I said. Let's say we want very small, it's actually very low resolution, 256, and then just a 224 samples per pixel. That already makes 14 million forward passes through MLP. It is too heavy, too slow, too many forward passes. So quite slow, empirically quite slow. Just a single scene, optimizing nerve of a single scene, just this drum, optimizing nerve for this drum, it already takes 1 to 2 days. And to optimize this one already take 1-2 days. And this one rendering less than 5 frames per sec. As I said, for the real-time application like a video game or movie, we need at least 20 frames per sec. 5 frames per sec is very slow. We cannot use it for real-time application. So although it has good strength, like topology free, does not require 3D geometry supervision, it is too slow. But the people invented many algorithms followed by original nerve. This is from Instant NGP from NVIDIA, 2022. Visual qualities, and I think this video is compressed, so visual quality is not very good from the compressed video, but it only takes, I think, a few minutes instead of a few days. Very fast compared to original nerve, but I'm still not very good actually. So, and one thing is that it is only for a, where is it? Only for a single scene. Here I introduced this one. Only for single scene. Single scene. Because the neural network only takes position and view direction, right? The neural network has no idea where this object, information of this object is not passed to the neural network, right? So only position and view direction is passed to the neural network. So it is only for a single scene. We optimize nerve for this drum. We optimize another nerve for this object. We optimize nerve for this microphone. We need to optimize nerve for each individual object or scene, right? That is what nerve is about. Only a single scene. You can replace only a single scene. So what we need to train nerve is multi-image of single scene and free image of a single scene. Once nerve is optimized for this drum, then this neural network is only dedicated to drum image rendering. It cannot use for other object rendering. So we need to train neural network for each object individually. Neural network for this drum, for this bottle, for this microphone. We need to optimize nerve separately for each scene. And as you can see, object is not moving, right? Human is not moving, object is not moving. Although we can change viewpoint, the entire scene is static. So there can be actually many extensions of this nerve, and actually many of them are already happening. Dynamic scene, moving object. How can we get moving object nerve? That is 4D, right? 4D nerve. Or inside of nerve or 3D, any 3D stuff, how can we animate them? How can we animate human? How can we make her lift her arm? How can we change her leg? How can we animate her? Or lighting. How can we introduce lighting? This one is daytime, right? How can we make this nighttime? How can we make this like a concert lighting? Introduce very shine light. How can we change light? Or how can we insert some object? Let's say I want some dog here. I want my dog here. But how can we insert dog in the optimized nerve? How can we do that? Real-time rendering. As I said, nerve is quite slow, only slower than 5 frames per sec. Not suitable for real-time application. How can we make a real-time render? And so as I said, nerve is optimized for each scene separately. A nerve for this drum is only for drum image rendering. Nerve for this scene is only for this scene. But how can we make some generalizable system that, I mean, for example, just take a single image and some neural network and then output nerve of this image. How can we do this? Instead of optimizing nerve separately for each scene, if we can design this kind of system, just to pass a single image or multiple images and then it instantly outputs nerve of this 3D scene, then we do not have to optimize nerve for each scene separately, right? How can we do that? Or generate instead of capture optimize. Now we need to prepare multiple images and then optimize nerve. But instead of this kind of capture optimized, how can we generate nerve from text? Texts are very easy to get, right? How can we generate them? There are many extensions. All of them are already happening. Maybe we cannot cover all of this stuff in this course, but these are possible extensions of nerve. Very important for real-world applications. Okay, this is end of today. And any questions? And